Lesson 1.3, Evaluating Limits Analytically. Your objectives: you will be able to use the properties of limits, find limits algebraically and using direct substitution, and apply the squeeze theorem. So the last lesson, 1.2, we were doing limits, but we were looking specifically at tables and at graphs and asking ourselves what seems like it should be there as we approach this our interested x value from both directions. Today we're going to look more at the properties in the algebra of limits. On your next slide, we have several properties of limits, and if we read through this, the information up top says B and C are real numbers. We can just think of them as some number for now, as well as n. Just think of B, C, and n as numbers. F and G are functions with the following limits. So as we approach C in both of these functions, the limit for f of x is L, limit for g of x is k. So these properties, 1 through 5, are all basically good news, meaning the properties of limits work like we want them to. For example, if we have a scalar multiplier for this one, b is our scalar multiplier. Remember, that's just a number times a function of x. If we're taking a limit, we can actually just take the limit of f of x and apply that scalar multiple to it. So it's kind of like you can slide the scalar multiple out of the limit and then just reapply it with multiplication. Kind of like undistributing, or I guess unmultiplying would be more appropriate. On the next one, sum or difference. So if we take a look at, if we have a sum or a difference of f of x plus g of x, again, we can just take the sum or the difference of their two limits. Okay, so on the product rule, we can just multiply the two limits. Quotient, again, we can just divide the two limits. And of course, we always have this fine print like that. We can't divide by 0. And the power rule. So again, all of this is good news for us because this is going to behave as we would hope it to. On the next slide, we have some theorems from our book and when we can use direct substitution. So theorem 1.3 is talking about the limits of polynomials and rational functions. The first part says if we have a polynomial function and c is a real number, then what this says right here is the limit of p of x is of p at x is equal to p of c as x approaches c. So basically what this is saying is if you think about any polynomial, a linear function, a quadratic's parabola, a cubic, a 4th degree, 5th degree, 6th degree, 7th degree, you should know from college algebra that any polynomial function, regardless of its degree, is going to be continuous and have no problems, as in no domain restrictions. The higher the degree, it's just going to make it more curvier. So what this what this theorem is saying for this part is, well, there's no problems, so we can just plug that c value in, and the limit is going to exist and be the actual value of the function. Remember, this is what happened on 1.2, and I told you that this actually catches kids off guard because they're expecting to evaluate limits where there is a domain restriction, a hole, an asymptote, or something like that. The second part is saying, well, the same thing is true for a rational function. So to your right, you can see I've got some rational function. Vertical asymptotes are happening at apparently x equals 1 and x equals -3. And this is, again, saying the same thing as long as we do not have a domain restriction. So when we divide by 0, what we were looking at a little bit last in lesson 1.2 is where we run into holes or asymptotes is when there is a division of 0. So the rest of this theorem is saying, well, anywhere that's not a problem, we can go ahead and do direct substitution. So for example, on this graph, assuming that there is no hole at x equals 4 that we can't see, it says, well, you can just figure out the limit at x equals 4 by plugging in the function x equals 4, and it's the function value. so on and so forth with, so this works for polynomials and rationals, and also we see down here, same thing with trigonometric functions. And again, it says a number in the domain. So over here we have what apparently looks like a cosine graph, but you guys probably know that some of these other trig functions have vertical asymptotes, domain restrictions, stuff like that. So those are domain restrictions, meaning as long as it's not one of those domain restrictions, we can go ahead and just plug in that x value and get the same as the limit. So on this slide, we're going to demonstrate using the properties of limits. And again, we want to try and do as much of this as possible without a calculator. So we'll take a look at this first example here. Limit as x approaches 2 of 3x squared plus 5x. So again, we probably notice that this is a polynomial, a second-degree polynomial, where we could actually just use direct substitution and plug x equals 2 in, and we're going to get the same answer as if I use limit from the properties of limits, property number 2, which says that I can take the sum of these two functions and I can add the same limit. Sorry, trying to think and write. What I mean is I can apply the limit to both of those components, the first part and the second part, and just use this addition. Okay, now we take a look at this, and again we have a quadratic function here, and we can go ahead and plug x equals 2 in. There's no problems with that. So when I plug x equals 2 in, I get 3, plugging in 2 squared, and again on this part right here, there is no problems with 5x at x equals 2, so I can go ahead and plug in 2 right there as well. So let's see, we get 4 times 3, that's going to give us 12, plus 10, so we get 22. Now again, we would have gotten that if had we just plugged in 2 to the original polynomial up here. You can verify that quickly probably, but I wanted to demonstrate using property number 2. Okay, for the second example, so we're going to call this our second, and I'm going to need some more room, so I'm going to erase our previous work. And here we have a rational function, and if we take a look at this, we notice that we're interested as x is approaching -1. Well, we ask ourselves, is there a problem with x being -1? And we can see at the top, if we plug in -1, we're going to get a 0 in the numerator, and that's not a problem for us. Our problems are coming from 0 in the denominators. If we plug in -1, we're not going to get a 0 in the denominator. So this is an example where we can use direct substitution and plug in -1 where we see an x. So there's our top over our bottom, and we can simplify. Top we get 0, bottom we get -3, 0 divided by -3. We get our limit right there. So this is an example of the last slide. We had those theorems that said if there's no problems, you can go ahead and use direct substitution. Now again, you can use your grapher and check out the tables, or look at the graph and zoom in, however you want to think of that, and there's going to be no problems, and it should agree with what we just found right here. So the last one, number 3, is a little bit more interesting, and maybe a place where we really benefit from some of these properties. So if I think about the graph shape of x times cosine of x, nothing comes to mind. I kind of know a little bit about the cosine of x, but all of a sudden when I multiply by x, then I don't really have a quick idea of what that graph looks like. So we know something is, sorry, let me use another property of those limits. So I'm going to kind of work over here, and I'm going to use that product property that says if I have the product of two functions, x times cosine x, those are x would be the first function, cosine x the second. Then I can split that apart, go to the same limit value of the first, and then I can multiply that by the same limit of the second. So the product property of limits allows us to rewrite this like that. Is this better? Well, I have a much better idea of what's going on with this part because I have the linear function y equals x, and as x approaches pi, there's no problems with y equals x, so I can actually at this point use direct substitution right there. So that's this part times this other part. Now I have the cosine of x as x goes to pi. All right, so I got to review a little bit of trigonometry. I'm going to go off to the side here and remind myself, what does a cosine of x look like? I like to use a graph, sometimes a unit circle, other times just kind of hit and miss with what I want to do. So I know the cosine curve does a full cycle at 2 pi, and I'm interested at pi, and I can really quick use the symmetry of this graph and say, oh, I know when cosine of x is pi, I'm getting the output value, the y value of -1. So this whole thing goes to -1. So our answer, let me go back and put my equal signs, is negative pi is the answer to limit for number 3. So that last one was a better example of when we would use the properties of limits. If we're taking a look at a function and we're thinking about its graph or whatever, table, numerical, however you want to think about it, it's a lot easier to break that one up and think about it, the chunks independently. So on this slide, our direction or our heading says evaluating limits algebraically. So what I want you to do is stop the video here and see what you can do in terms of factoring, or just think about these limits and what do you know about them. So I'll give you a moment to do that. So on the leftmost example, I did my factoring and I got the following expanded factored form of that numerator. And as we can see, that again, I can't plug in x equals 3, it makes a 0 in my denominator. However, algebraically, the numerator and that denominator are going to cancel, and we're going to get this new limit as x goes to 3 of what's left in the top. So the bottom canceled to 1, and we get x plus 4 as everything left on that. Now at this point, we can say, well, if we're interested as x approaches 3, there's no reason we can't just plug 3 in for x right there. So on the next step, I'm going to evaluate this limit operation, plug in 3 for x, and we get our answer of 7. So one thing I want you to notice in this process is we started with a limit. This thing is a math operation. So one thing that kids kind of get sloppy about is as they work it through the problem, they don't want to keep it with, and they just want to kind of apply the limit right at the end. And you will get graded off for that. So just like if you were to write 3 plus 4, yada, 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 in some equation, and all of a sudden your 3 plus 4 just turned into that, we would know that's not acceptable, and that's definitely not what we want to do. So again, this is a math operator, and it doesn't just get to go away for your convenience. We need to carry it through the process. So with this example that we've just worked out, if we were to think about this graphically, the fact that this term, oops, I'm still in red ink, that's okay, that term canceled out actually informs us about what type of domain restriction we have, or what this looks like in the graph. If it's a 0, the numerator and the denominator, that actually means it's a whole, not a vertical asymptote. So if you were to graph this, and you can go ahead and use your grapher, what this is actually going to end up looking like is a linear function that resembles the function y equals x plus 4. And why that is because algebraically, like I said, those two terms cancel out. And what this is saying is basically everywhere except for that hole, it's going to look like this function right there. So let's make a correction to our graph. I'm just going to scale a 4 right there and use my eraser. Whoa, big eraser. And now we know that there is actually a hole in this graph right there. So our book has directions, a set of directions for your homework that says, let me write it down, I'll be right back. Okay, the wording that our book uses is this statement: this function agrees with the given function at all but one point. What that means is this function that we found agrees with the given function, so the given rational function, at all but one point, meaning this rational is going to look like this linear everywhere except for when x equals 4. So these are kind of confusing phrasing that our book uses, but now once I've explained it, hopefully that makes sense. Now, kind of used a lot of this slide for that example, and that's fine, because if you notice on the right question, the limit as x goes to 1, again, one of the first things our brain wants to do is it wants to find the problem with this, and we see that we have a 0 in the denominator when x is equal to -1. So what our brain wants to do is actually work this limit incorrectly. It doesn't care about when x is -1. It's asking for something completely different. There's no problems when x is 1. So this is an example where we can just use direct substitution. So we can plug it straight in to the top. And the bottom. And we get 1 plus 1, so we get 4 halves, or 2. All right, so notice again, the limit notation disappeared on this step right there because I did the direct substitution of that limit. And again, a common misconception is students will often work this limit incorrectly for where they see this problem happening. Their brain just kind of tricks them and says, well, we want to go to where there's a vertical asymptote or a hole. We override this concept of it's not caring about that for this question. So we've got 2 more examples here, and again it says evaluate limits algebraically. So I'm going to have you pause the video here, see what we can do algebraically. Keep in mind, if we can use direct substitution, as in if we can just plug that x value in because there is no problems, then don't waste your time on factoring. You can actually go straight for it. So take a moment, see what you can do algebraically on these 2, and after you